Next on our laundry list of reactions for the alkenes is a reaction called hydration. Relatively simple, as you can probably figure out, involves adding water. But that's not going to happen easily. So if I take a simple alkene and I put water near it, this basically accomplishes nothing. It's not going to react under those conditions. The alkene is not susceptible to nucleophiles directly. I have nothing really electrophilic here to work with, so I'm out of luck. But if instead I give it some acid, not particularly concentrated, so this actually works pretty well with fairly dilute acid, then it will actually work. And it works mechanistically very similar to what we saw in the previous example, and that is that we're going to see the alkene acting as a base first. So something like this. So we have the hydronium ion and the base taking that, which leads us to that same decision point that we saw in the HBr addition, which is I have two possible cations coming out of this. One, I have a cation on the internal carbon here. And two, I have a cation on the external one, where the incoming hydrogen, if I circle it, ended up either here or on the internal one in this case. Now, as with many of the examples, and I said in the previous video, we need to kind of think what's reasonable and what's not. And again, I've chosen this loaded dice case example. As I said in the first video, there's nothing magical about it. It's just a case where I can look easily at the difference between the two carbons. So we basically are never going to see this. It is not going to happen. We're not going to see a primary cation unless we have some other stabilizing force. In this case, we don't. We will see tertiary cations quite readily. Now, in this case, though, I don't have a great nucleophile left around. I don't have a bromide ion the way I did in that first example that we talked about. All I have here is water. So we're looking at water as a nucleophile. Well, generally, that's not so good, but we have seen it before. We've seen it before in an SN1 reaction where we only had weak nucleophiles, but we had that cation to help us. Oh, look, it looks just like this. Yes, we still have a cation because we're getting at it a different way, but it's the same principle. At this point, we're looking at SN1 type mechanisms. So this is planar. It's susceptible to attack even by a weak nucleophile. So that's going to give us this intermediate structure where we have a cation and we have the hydrogen that we brought in earlier on the adjacent carbon. So just to clear up what's happening there, because we'll see this in a lot of examples as we move forward, is that if I have a protonated alcohol like this, so like what we just got out of the reaction, and again, I'll just label this for clarity. That is a very simple equilibrium with water. Water will take that as a base. The alcohol, roughly the same Ka, will give that up as an acid, so it's equilibrium driven. So I have this now, a neutral alcohol, my product, my hydrogen that I added here, and the two methyl groups that were there before, and I'll have this. So as my other byproduct. Well, remember that we're talking about anything that involves water as a nucleophile or the hydronium ion. Water is the solvent. So just to keep that in mind, water is pure concentration in and of itself is 55.5 molar. So if this is an equilibrium, that is one hell of a push to go towards the right side. We have a massive amount of water compared to the concentration of anything that's ever going to be in it. So while it is technically an equilibrium, this reverse step is not like this. And sometimes you'll see that drawn like this. I don't want to go back and erase it here, but sometimes you'll see it drawn like this to imply that the reverse step, while it exists, is kind of not realistic. And that's the case here. This is driven very far to the right by the fact that water is the solvent. So this reaction has a lot of problems, though. acid and alcohols together tends to cause problems. Depending on specific examples, we could also cause rearrangements, we could cause polymerization, we could cause ethers to form. So this is not, generally speaking, the greatest of reactions to use to do this reaction with. We're going to talk about some other ones in the next video.